Stanford University.
We did not talk about Helmholtz free energy, did we? We did? What did I say about Helmholtz free energy? Just a definition, that it's the logarithm that's related to the logarithm of the partition? That's all? Okay, good. Oh, we never got to the ideal gas at all? No. My problem is I'm teaching this course both in graduate school and here, and I'm completely for... Did we prove the following identity? Oh, we didn't do that either. Okay, let's assume that for now. Oh, I thought we had done the ideal gas. Okay, before we do the ideal gas, I want to get to the ideas of volume and free energy. We'll need it. So let's define a concept. I think I told you last time that the logarithm of the partition function, or is there a minus sign? I think there's a minus sign. T times the logarithm of the partition function is called the Helmholtz free energy, A. Okay. The Helmholtz free energy has an important meaning, but before we get into its, or important usefulness, before we get into it, did we prove, all right, you're going to have to help me out. Did we prove the relationship between energy, free energy, and entropy? Yeah. We did. Oh, good. So we don't have to do that. Okay. In particular, temperature times entropy minus the energy is equal to the free energy? Okay, we did that. Good. I'm all bollocksed up because of my confusions about what I'm teaching where. Okay, so we don't have to do that. Did we talk about control parameters at all? Oh, we did fluctuations, but we did not do control. Okay, before we do the ideal gas, I would like to introduce the concept of pressure and how you calculate the pressure in a system. This is still more theory and less application, but still, if we want to do the ideal gas, I think we better know what pressure is. Okay. The definition of pressure is, of course, through the definition of force on the walls. We could imagine, if you like, a cylinder with a piston, and we could measure the force on this piston due to the collisions of the molecules with the piston, and that would define the pressure. The pressure is the force divided by the area of the piston, force divided by area. I don't even think I'll bother writing that down. We all know that. So the question is, how do we calculate the force on a system? Well, we could try to calculate the collision with the molecules. Every time a molecule bounces off, it makes a sudden force on here, an impulsive sudden force. We could average the force over enough time so that the actual force is a very, very wiggly function that jumps around a lot. We could average it over time and define a pressure in that way. That is not a particularly convenient way to define pressure, nor is it a very general way. Molecules hitting walls are not the only way that you can get pressure. Another way, for example, you could get pressure is there might be direct forces, not just collisional forces, not just contact forces of the molecules with the walls, but there might be a potential energy, a long-range force of some kind. Maybe not long-range, but semi-long-range force between the molecules and the piston. And they might push or pull on the piston. And that would not have to do with direct collisions. So we need a more general definition, both of force in general, but in particular force on the piston in this particular setup. Right? Now, let me remind you what the definition of force is in mechanics. The definition of force in mechanics is the change in the potential energy of a system with respect to position, right? Or the change in potential energy with respect to some coordinate. Let's write down the formula just to remind you. The change in the potential energy, let's write potential energy, let me call it U, with respect to a coordinate actually is minus the force. Okay. Now, that suggests that we define the pressure or the force on the cylinder here, on the piston, as the change in energy of the system with respect to motion of the piston. We can either think of the change, that's a good way to think about it. The change in the energy of the system, how much does the energy of the system change when we move the piston a little bit? Another way to think about it is the work done on the piston per unit position change, right? The work done. So if we can calculate the change in energy, now what will that be? That will be the change in energy minus the change in energy of the gas in here as we change the volume. We change the volume a little bit, the energy in there will change, and that is the work done on the piston. It's also minus the work done by the piston on the gas. Energy conservation tells us that the work done on the piston by the gas is the same as the work done on the minus sign, the work done by the gas on the piston. So, and we'll focus on the work done by the piston on the gas. So we can imagine squeezing the gas a little bit, changing the volume or changing the coordinate of the piston, and the work done on the gas, or the change in energy of the gas with respect to a small motion of the piston, is of course called the force on the piston. Is that clear? All right, so that's a definition. The change in energy, we call it delta E, divided by delta x, where x could be the position of the piston, x. That's the force on the piston. It's important in this context that we move the piston slowly. Why? Let me give you a crazy example. Supposing, let's move the piston outward, okay? The formula is still true. The change in energy of the gas with respect to the location of the piston is related to the force. Right? Supposing we change the position of the piston really fast, so fast that we were moving the piston faster than the velocity of the molecules. What would be the force on the piston when it receded very quickly away from the molecules? 0. Why? Because no molecule would bang into the piston, and so there would be no force. So it's important that we move the piston slowly so that some average of the collisions can be averaged over. So we move the piston slowly, adiabatically is the word. We move the piston adiabatically, and we calculate the change in energy with respect to position. Now, if we multiply this by the area of the piston, I shouldn't call it A because that's going to be free energy. Let's call it little a. This becomes the force divided by little a, the area of the piston. And what's little a times delta x? That's the change in volume. All right? The area of the piston times the change in position of the piston is the change in volume. So we could write that the change in energy divided by the volume is the force divided by the area. What's the force divided by the area? The pressure. Now, I have a feeling I have the sign wrong, and I'll tell you why. It's a question of keeping clear in your head whether we're talking about the change in the energy of the gas or the change in the energy of the position of the piston when it's pushed. All right. If I squeeze the gas, do I increase or decrease the energy of the molecules inside? You increase it. So just to check which the right sign is, I'm thinking of E now as the energy of the gas, not the energy of the piston. All right. If I move the piston inward, I decrease the volume. Is that correct? All right. But the pressure is positive. All right. Delta E is positive. Delta V is negative. So delta E divided by delta V would be negative if I squeeze the gas a little bit. But that must correspond to positive pressure. So there must be a minus sign here. And there is. All right. So the change in energy per unit volume is minus the pressure. That minus sign always seems a little peculiar to me, but it's right. And as I said, that's the way to think about it. Squeezing the gas decreases the volume but increases the pressure. Okay, now, again, we must do it slowly. Otherwise, the point is that pressure is a concept that is, again, an average concept, averaged over some time. So you can't do it instantly fast. You better do it slowly. And what's more, what's also important is that in this formula, that the only changes in energy are due to the motion of the piston. I can imagine other changes. I could imagine that while I move the piston a little bit slowly, I could heat the gas by putting a flame under it. Okay? Let's see, or cool it, or take energy out of it. Then this formula would not be right. For example, I could squeeze the gas a little bit, which would tend to increase the energy, but at the same time remove heat from the gas, right, by connecting it to a refrigerator. Right? I could decrease the energy by removing heat, but squeeze the gas, which would tend to increase the energy. The net effect being, if I tuned it correctly, to not change the energy at all. Then I would have a change in energy and a change in volume, but it wouldn't give me the right answer for the pressure. In fact, it wouldn't necessarily need any pressure to do that. Okay? You just change the volume, remove heat. You don't need any pressure to do that. In fact, if you remove heat, the volume will naturally change by itself. So it's important also that you not have any other sources of energy coming into and out of the system other than the work done by moving the piston. Okay, no heat allowed in and out. You move the piston slowly. What is such a process called? Adiabatic.
Couldn't you also just say that, well, there's a pressure term and then there's another term?
Sure, we'll do that. But we want to first define pressure. Before we write that there's a pressure term and another term, we've got to define pressure. Okay, now, adiabatic also means a constant entropy. Have we discussed that or not? I don't remember. We haven't. All right, so let me explain to you why an adiabatic process, that means one done slowly, why that is a process at constant entropy. This really ultimately comes from quantum mechanics. It can be phrased in terms of classical mechanics, but it's easier to phrase it in terms of, well, we don't even need quantum mechanics. We don't need quantum mechanics. All we need is the idea that there are energy levels and that the energy levels are discrete. Now, this is the energy levels of a system, but let's plot horizontally the volume of the system. So here we are. There's a system. It has a collection of possible energies. the energies just being the sums of the energies of all the particles in there. If we were doing quantum mechanics, the energies would be discrete. If we're not doing quantum mechanics, then we have to be a little more careful. But in quantum mechanics, we have discrete energy levels, and we can label the ith energy level. Horizontally, we have the volume of the system. The energy levels are not independent of the volume of the system. If you change the system by changing the volume, the energy levels will change. For example, if you slowly change the volume of the system, then the values of, I don't mean the energy itself, I mean the values of the possible values of the energy levels of the system, the possible values of the energy, they will also change. For example, if you have a box of a certain size, if the size is very small, the energy levels are very, very well separated. This is a quantum mechanics fact. A small box, it takes a lot of energy to jump to the next level, the next energy level. A large box, it only takes a small energy to jump to the next energy level. So as the volume changes, the energy levels themselves, the individual values of the energies of both a single particle or just a whole system, they also change. So let's imagine plotting them as they change. The energy levels evolve. Typically, as you make the system bigger, the energy levels decrease, so I've indicated them by a decreasing function. And so forth. No, not particularly. No reason for that. On certain situations it might be, but in general, it's typically, again, it doesn't have to be any particular kind of function of volume. But there are two important properties. They are connected to the issue of conservation of information. You can think of the changing of the volume, the slow changing of the volume, as the time evolution of a system. What do we know about the time evolution of systems in both classical mechanics and quantum mechanics? Number one, no level disappears. The energy levels just evolve and they don't disappear or reappear. No new energy levels appear as you change the volume or any other control parameter. A control parameter means a thing that you can dial slowly. As you slowly dial a control parameter, I'll give you other examples of control parameters, but the volume is the most familiar one. The energy levels don't disappear, and number two, they don't cross each other. They don't cross and they don't disappear. They stay in the same order. So the lowest energy level stays lowest, the next one stays second lowest, and so forth. That is a property of both quantum mechanics, and there's an analog of it in classical mechanics. Now, supposing we start our system at a given energy level, and we slowly vary the control parameter. What happens? There's a theorem about this, and the theorem is called the adiabatic theorem. It's a quantum mechanics theorem. There's an analog of it, as I said, for classical mechanics. The quantum mechanics theorem says that the system, as you very slowly change the control parameter, the system will remain in a state of definite energy, and it will just track along these lines. So if you start the system over here with this precise value of the energy, and if you know the shape of these curves, you vary the volume slowly, you know that you'll wind up over here, again, in a precise energy level. What happens if we know, let's suppose our state of knowledge in the initial state is such that all we know is that we start in one of these three levels. One of these three levels, that's all we know. Then, after a period, we know that we're still in one of these three levels. That's all we know. Okay? What happens if we know that the probability for being in one of these three levels is 1/2, 1/4, and 1/4. 1/2, 1/4, and that does sum to 1, doesn't it? Yeah. 1/2, 1/4, and 1/4. What will the probabilities for being in the different levels over here be? 1/2, 1/4, 1/4. What happens to the entropy if we start with a given entropy here? It does not change. Why? Because the probability distribution doesn't change. The probability of being in the ith level doesn't change. So we can say that P of I is an adiabatic invariant. That's the terminology. An adiabatic invariant means a very slow change. The probability of being in the ith state, even though the energy of the ith state may change, the energy of each of these states change. How can that be consistent with energy conservation? Because we do some work by changing the parameters. Exactly. We do some work by changing the parameters. So the levels change, meaning to say the energy levels change, the energy that they have, but the probability of being in the ith level doesn't change, and that assures that the entropy, which is after all just the summation of p sub I log p sub I, you know what I mean, p sub I, that doesn't change. So the entropy is an adiabatic invariant. Let's come back now. Now this is really central, that energy is an entropy is an energy is not an adiabatic invariant. Entropy is an adiabatic invariant, and the ultimate reason for it is information conservation. Without it, we could have energy levels running into each other and all sorts of funny things happening, and the probability distribution would not be an adiabatic invariant. Okay, let's come over to here now. We said that the pressure was the rate of change of energy with respect to volume with a minus sign in an adiabatic process. We now know that that means at fixed entropy. At fixed entropy. So the definition of pressure, let's write it as a calculus equation, minus the pressure is the derivative of the energy with respect to the volume, keeping fixed the entropy. Now, keeping fixed not keeping fixed the temperature, certainly not keeping fixed the energy. The derivative of the energy with respect to the energy is what? 1. It's certainly not the derivative of energy with respect to energy. Sorry, I forget what I said. The derivative of energy with respect to volume at fixed something defines the pressure. The something is the entropy. Okay. Think of fixed entropy as, first of all, again, meaning do it slowly so that you have time for things to average, but also without adding other forms of energy to the system that you haven't accounted for. Then that's not having to do with this pressure. Then this is the definition, and that is the definition of pressure. There's a more general concept, which I might as well tell you. There are other kinds of control parameters besides volume. Let me give you an example. External magnetic field. Again, you could imagine a dial that ramps up current, or external electric field, which is a dial that ramps up the charge on capacitor plates, or anything like that. Those are also control parameters, and those control parameters also, when you change them, do work on a system. Same kind of formula, and you could write it more generally. Instead of volume, we could introduce a control parameter x. Volume, replace it by x, whatever x is, magnetic field or anything else. Instead of pressure, let's define the variable y that goes with x. The definition of y is simply minus y is equal to the derivative of energy with respect to x, whatever x is, at constant entropy. So there are lots of things like this. The most familiar, and we'll mostly work with this, the most familiar being volume and pressure. These variables come in pairs. They come in pairs. Y, which is the general force, if you like, the derivative of energy with respect to x, and x. They're called conjugate thermodynamic variables. The most familiar, again, pressure and volume. The question is, how do we calculate the pressure? Well, that's not so hard. All we have to do is figure out the energy as a function of the entropy and the volume. And energy as a function of volume and entropy, and then we can differentiate keeping the entropy fixed. But calculating the entropy of a general system is usually difficult. It's usually a pain in the neck, frankly. You can do it, but there's a simpler formula for the pressure. And the simple formula involves not the rate of change of energy with respect to volume at fixed entropy, but something else. This is also equal to the rate of change of something else with respect to volume at fixed temperature. Why is it easier to be able to deal with fixed temperature? The reason it's easier to be able to deal with fixed temperature is very simple. When you write the partition function, everything goes back to the partition function. All right? You calculate the partition function. It's handed to you as a function of temperature. That's the natural variable. That's the variable that the partition function is directly presented to you as a function of. And if you can differentiate the appropriate thing with respect to volume at fixed temperature, it's usually much easier than first having to calculate the entropy and then trying to differentiate something keeping the entropy fixed. It's usually much more difficult. Right? This is easier. What is the thing that you differentiate? The Helmholtz free energy. And the Helmholtz free energy, that's not so hard. Once you know the partition function and its logarithm, you multiply it by the temperature, and then you differentiate the Helmholtz free energy with respect to the volume. All right, now I haven't told you why that's true. So, since I don't like leaving loose ends, we should prove the theorem that says, let's see what it says. It's a little mathematics theorem, not very hard. Well, it says that the derivative of energy with respect to volume at fixed entropy is the same as the derivative of the free energy. Sorry, there should be a yeah, same thing, no, sorry. It's the derivative of the free energy with respect to the volume at fixed temperature. All right. In order to prove this, we need a little bit of a theorem. It's a small theorem. It's a calculus theorem. It's practically not a theorem. It's just a simple identity. And let's see what the theorem is. Let's plot two independent. Any questions? No questions. All right. So let's plot horizontally the volume, or it could be any other control parameter. The theorem I'm going to teach you, which is in the notes, you can apply to any control parameter at all. But let's take the volume as our special case. And vertically, let's see, what did I plot vertically? I think the temperature. Yeah, the temperature. And now let's imagine drawing the lines. Let's see, we need the lines. Let me see what lines we need. Well, let's first start with a point. All right. Now, this point, at every point, there's a value of energy and also of entropy. The temperature, if you know the temperature and you know the volume, you know everything about the system, and you can compute the energy and the entropy. Let's see, I want to make sure my diagram looks consistent with the one in my notes. So yeah. All right. We can also draw lines of constant entropy and energy. Right. What do they look like? I don't know what they look like, but let's draw in just some arbitrary lines. Here's a line of constant energy, and let's put in a line of constant entropy right through that point. Okay. So the entropy along this line is constant, and the energy along this line is constant. S equals constant, S equals constant, energy equals constant. Now, what do I want to compute? I want to compute the rate of change of energy with respect to volume at fixed entropy. That's the pressure. That is the pressure, or minus the pressure. All right? But I would like to compute it in terms of derivatives with respect to temperature. I want to compute it in a different way. All right, so what are we computing here? Let's take a differential change in volume. Here's a differential change in volume dV. This is the change in energy when I change the volume a little bit, keeping the entropy fixed. So it's the difference between the entropy at the energy at this point and this point. Is that clear? If that's not clear, we might as well not go any further. The rate of change of energy when we change the volume a little bit is the difference between the energy here and the energy here, divided by dV, of course, divided by dV. Here's how I'm going to calculate it. I'm going to calculate the change in the energy when I go horizontally, that's at fixed temperature, and then when I drop down vertically. So the change in energy in going from here to here is the sum of two terms. The first is the change in energy at fixed temperature. This is the change. This should be partial derivative. Partial derivative of energy with respect to volume at fixed temperature. That's this change here. And then there's the vertical change. Okay. What is the vertical change? Well, in going from here to here, the entropy changes. Why does the entropy change? Because the entropy is different over here than it is over here. The entropy was constant along here. It has a different value. Let me use a different color. The entropy has a different value over here. And so we can compute the change in the energy going from here to here as the change in the energy with respect to the entropy, we're changing the entropy a little bit, times the change in the entropy when we go from here to here. The change in the energy with respect to the entropy times the change in the entropy will give us the change in the entropy. All right? So we have to multiply this by the change in the entropy when we change what? When we go from this curve to this curve. It doesn't matter whether we go from this curve to this curve from here to here or from here to here. Why? Because the entropy is constant along these lines. Right? So the change in the entropy, the energy, is the change in the energy per unit volume at fixed temperature, that's the horizontal change, plus the vertical change, which is the change in the energy with respect to the entropy times the change in the entropy in dropping down vertically. What's the change in the entropy in dropping down vertically? It's the change in the entropy dropping down vertically. change in the entropy with respect to the temperature at fixed volume. Fixed volume is vertical.
Why wouldn't you use the other way around? Change the volume.
What's that?
Couldn't that be ds dv and fixing t?
ds by d.
dv. You know,
We're not changing the volume going down.
no, I mean, you said that it's the same whether we go down or we go left.
Yeah. It's the same whether we go down or we go left. I happen. What's the question?
The question was, then both of them would have fixed the temperature.
You could use either one.
Okay.
We can use either one. Okay. Okay.
Yeah. Well,
No, okay, good,
that
good,
doesn't seem
good.
to be good.
What is this? This is dE by ds at fixed something. dE by ds at fixed x. Sorry, at fixed volume.
Oh, okay. So yeah.
Yeah, at fixed volume. Okay. dE by ds at fixed volume times ds by dt at fixed. No, I've got something wrong here. ds by dx at fixed temperature. ds by yeah, dE by ds at fixed volume, ds by the volume, I'm sorry, ds by dE,
You can only fix one of them.
wait, dE,
I just think
dE by ds at fixed volume times the change in s in going from here to here. The change in s from going to here is the s by the volume at fixed x, at fixed t. I have too many variables in my formulas. All right. The change in going from here to here in the entropy is the change in entropy with respect to volume at fixed temperature. That's the formula that we want, I think. Yeah, that's the formula that we want. Okay, now.
Would you make that clearer again?
Yeah, I will. All right. We have this, which is dE by the volume at fixed temperature. Okay? Or better yet, let's just write dE. Let's not even write dE dV. The change in energy in going from here to here is the derivative of energy with respect to volume at fixed temperature times the change in volume in going from here to here, right? That's one term. That's in going from here to here. And then vertically going downward is minus the derivative of energy with respect to a change in the entropy. The entropy here and the entropy here is different. At fixed volume, that's because I've dropped vertically, times the change in the entropy in going from here to here. And that's it. In this formula, you can think of volume and entropy as the independent variables. Change in energy with, temperature and volume. Derivative with respect to energy, derivative of energy with respect to volume, keeping temperature fixed. That's horizontal. Then derivative of energy with respect to entropy at fixed volume times the change in entropy in going from here to here.
Total change in energy. E is a function of B and T in the first partial E with respect to B. And it's a function
In this formula, you can think of the energy as a function of volume and entropy.
Okay, so then
Yeah.
What do you mean by holding temperature constant? I guess is a combination of volume.
Yeah, yeah, yeah. But whatever it is, it's the change in energy with respect to volume, keeping the temperature fixed. That's the coefficient that goes with volume. And the other one is derivative with respect to entropy times the change in entropy. Why? Because you're going from here back to here rather than from here to here. You're going from here down to here. And so the sign is negative. Sign is negative. You just spend some time with it, and you'll see why why it's negative. Okay, now, what is the change in entropy in going from here to here? That's this over here. The change in entropy in going from here to here is also the change in entropy from going from here to here. You know, you're right. It really is positive. The change in entropy in going from here to here is the same as the change in entropy in going from here to here. But that's minus the change in entropy of going from here to here. That's where the minus sign comes from. In going from here to here, so it's the change in entropy in going from here to here, and that involves a minus sign. This ds is the change in entropy in going from this point to that point, which is minus the change in entropy of going from that point to that point. Okay, what's the change in entropy of going from here to here? It's the derivative of the entropy with respect to the volume at fixed temperature. That's the change in entropy going from here to here. At fixed temperature, yeah. Times dV. No, it's not equal to 0. It's a change in energy in going from here to here. That's what it is. Right? Now if I divide it by d volume, then I get the derivative of energy with respect to volume along this line, which is constant entropy. That's equal derivative of energy with respect to volume at fixed temperature, dV, minus the derivative of energy with respect to entropy at fixed volume. Say it again? Yeah, take the dV out. I have a certain threshold. When the symbols just get too many, I just really lose them. The EdV at fixed temperature minus the E ds at fixed volume, ds by dV at fixed temperature. That's my first line, yeah. I just rewrote it. Okay, now why is it interesting? This is the thing. Oh, incidentally, this is a calculus theorem here. I haven't used the interpretation of these variables yet. This is a calculus theorem about relationships between derivatives with respect to two different variables. So it's not a deep theorem about energy and entropy or anything else. It's just the calculus theorem. Okay, now let's apply it to the real thing. What is the derivative of the energy with respect to the entropy at fixed volume? Now, at fixed volume, we're talking about a system with no change in the control parameter. It's just the same kind of system we studied before we even talked about control parameters. Do you remember, before we introduced control parameters to do work on the system, do you remember what dE by ds was? Temperature. So now we use some physics. Now we're going beyond calculus, and we can write that dE by dV at fixed S, which is the pressure, which is minus the pressure, that's the thing we're trying to calculate, that's equal to dE by dV at fixed temperature. Well, it's a lot easier to calculate things at fixed temperature than it is at fixed energy, so that's a good sign. All right? I just rewrote this over here. And then minus, but this is just the temperature, dE by ds at fixed volume. Temperature times ds by dV at fixed temperature. All I'm doing is using a little bit of physics. The physics wasn't saying that dE by ds at fixed volume was temperature, and a little bit of calculus to write down this theorem. And I have succeeded in writing the pressure in terms of derivatives with respect to temperature instead of derivatives at fixed temperature instead of at fixed entropy. That is an advantage because it means you don't have to go and calculate the entropy and keep it constant while you're varying the volume. All right, but this is even simpler. This over here is the same as the derivative of Ts with respect to the volume at fixed T. Why is that? Because the derivative of T with respect to T, yeah. Yeah. Okay. So I can pull a T inside the derivative, and this is just the derivative of Ts with respect to volume at fixed temperature, and this is the derivative of energy with respect to volume at fixed temperature. The result is that this is equal to the derivative with respect to the volume at fixed temperature of E minus Ts. E minus Ts, and that's minus the pressure. Okay? These two terms combine together to just say they're both derivatives with respect to volume at fixed temperature, and the result is derivative of E minus Ts at fixed volume. Well, what is E minus Ts? It's A, the Helmholtz free energy. The Helmholtz free energy. So we now have a lovely theorem that says that pressure is equal to, let's rewrite it, pressure is equal to minus not the derivative of the ordinary energy, but the derivative of the Helmholtz free energy.
No, isn't that minus the Helmholtz energy?
This is the Helmholtz.
It's minus.
No, that is, you got minus on that one, but wrong.
It is minus the derivative. It should be minus the derivative of the Helmholtz free energy with respect to the volume at fixed T. I think I've got it right. Yeah. Okay. And that's an enormous simplification because the Helmholtz free energy is just simply related to the logarithm of the partition function. You don't even have to differentiate it. To get the energy, you have to differentiate the partition function. And to keep the entropy fixed, you have to calculate the entropy. So you'd have to do two procedures, one of which can be rather complicated. You have to, if you wanted to use energy and entropy, you have to differentiate to get the energy. And then you would have to keep the entropy fixed. And believe me, that's a nuisance. On the other hand, the whole theorem simply tells you to calculate the pressure, all you have to do is differentiate the logarithm of the partition function at fixed temperature with respect to the volume. So if you can calculate the partition function as a function of temperature and volume, you're home. You have the pressure. So that's what we're going to do. We're going to do that now for the free gas. Should we take a 5-minute break? All right. This is our fundamental equation. There's a more general version of it. There's a more general version of it where things like pressure are derivatives of the Helmholtz free energy with respect to other control parameters. But this is the basic one we're going to use, at least for today. What we're going to calculate is the pressure, energy, and all the various properties of the ideal gas. We now know enough to do that, and we can apply it to a simple statistical mechanical system. We'll take 5 minutes. All right, we want to apply our tools now. We have a lot of tools. Partition function, free energy, real energy, entropy. We have all these tools, theorems of various kinds, and we'd like to apply it to a simple system. The simplest interesting system, well, an interesting simple system, is the ideal gas. The ideal gas is a system of point particles which are non-interacting, no structure to the particles. We can modify that later. We can allow them to have some internal structure, but without any internal structure, point particles filling a volume V. And the object is to calculate all the thermodynamic properties of it by computing the partition function and then applying the various tools that we have. All right, now we have to, in order to do the partition function, we have to sum over states. There's a sum over states of a system. Here's our system. The states of a classical mechanical system are not discrete things like that. They're continuous. They're characterized by positions and momenta. That means that the sum over states is going to be replaced by an integral. I'm not going to spend a lot of time explaining that procedure, but what are we going to be integrating over? All of the things that characterize the state of the system. So if the system has n particles, capital N particles, then its state is described by 3n coordinates, namely the 3n positions of the molecules and the 3n components of momenta. That means that the sum over states will be replaced by an integral. Integrals and sums are, of course, the same thing in some limit. In quantum mechanics, it would literally be the sum. In classical mechanics, we have to bend our definitions a little bit to include the possibility of continuous sums and to characterize the state of the system, momenta, and position. All right, so what do I replace the sum by? An integral over the position of every particle. That means d3nx. 3n x integrations for each particle. Sorry, 3 integration for each particle, the 3 coordinates of space, x, y, and z, and the 3 components of momentum. I'll just indicate it that way. That replaces the sum. Now, what do I sum? Normally I sum e to the minus beta times the energy of the ith level. Instead, we're going to have e to the minus the energy, but not the energy of the ith level, but the energy of a state with particles at position x and momentum p. So what do we write here? We write the energy is the sum over all the particles in the system. There's a contribution to the energy from every particle. Let's write it sum over little n to indicate the particles. And what's the energy? If there are no forces between the particles, and let's also assume that there's no gravitational field or anything like that, it's just particles in a box, then the only energy is the kinetic energy of the particles. So it's the sum over n of p sub n, that means the nth particle, squared, divided by twice the mass, and that's it. Let me write that all on one line. Not 2 to the m, but momentum of the nth particle squared. And that, of course, means px squared plus py squared plus pz squared. So this is a sum over all the squared momenta, all 3n of them, divided by twice the mass. And I'm assuming all of the particles have the same mass. Now that's it almost. There's one other thing that needs to be taken into account. That's the following idea. We're going to assume that all of the particles are identical. You can't tell them apart. So let's imagine we have a state. I'm going to draw the particles as little disks. They're really point particles, but you won't be able to see them if I draw them as points. Little disks, the particles. Now, supposing I interchange these two particles, is that the same state or is it a different state? Well, now is a matter of interpretation, and not the interpretation. It's in fact, it actually doesn't matter in the end. But if they're really identical particles, and there's no difference between them, then interchanging two of them is the same state as before. Okay? So supposing there's only two particles, and I integrate over all possible states, I'm double counting. I'm double counting because I'm counting each configuration twice. If I call this the first particle and the second particle, this is the same configuration. This is not a Q, this is just a particle. This is the same as particle 2 over here and particle 1 over here. So that means I would have to divide by 2. What if there are 3 particles? What do I divide by? If there are n particles, n factorial. Right? So to keep track of the fact that the particles are all physically identical, that an interchange of 2 of them is a trivial non-change of the state, we put a 1 over n factorial in front of it. All right, this is what we want to calculate. That's the partition function, and it's z of beta. But it's also a function of the volume. Where does the volume come into this? Well, the x integrations are done over some range, and the range of the x integrations is the interior of the box of gas. Right? So implicitly, there's also a dependence. In fact, I mean, in principle, there could be a dependence not just on the volume, but the shape of the box. However, in this particular case, it's really only the volume that comes in, the temperature and the volume. Now, the integrand here does not depend on x at all. So that means I can do the x integrations immediately. And what does each x integration, supposing I focus on a particular particle, let's say the first particle, dx1, this is d3x1, what is that integral? It's just the volume. I have n such integrals, and so I get a factor which is volume to the nth. Volume to the nth divided by n factorial. Incidentally, volume to the nth over n factorial can be re-expressed in a neat way. I'll write it out here for you, but for the moment I'm going to leave it in the form that it is, but let me just re-express it for you. Volume to the nth, without the n factorial you couldn't do this. Volume to the nth over n factorial. Now what's Stirling's approximation to n factorial for large n? N to the n, not the n to the n, e to the minus n, right? The other way? No. All right. Which is equal to e to the n, v to the n over n to the n, which in turn, e to the n, that's just it's there, but it's e times the volume over n to the nth. Now, what is v over n? Or n over v? Density. N over v is the density. So in fact, this is E divided by the density, rho, to the power n. In other words, for each particle in the system, there is a factor of 1 over density in the partition function. We'll use that another time. I'm not going to use that today, but it's interesting to notice that this thing combines itself in together in such a way as to give a factor of 1 over the density for each particle. All right? That's a useful fact that'll come up another time. But for the time being, let's just leave it this way. The reason I want to leave it in terms of the volume, because later on I want to differentiate with respect to the volume to calculate the pressure. Okay, here's the entire dependence on the volume. There is no other dependence on the volume. And the rest of it is just this P integration. So we have to figure out how to do the P integration. And the P integration is actually easy. There are 3n identical integrals. In other words, it's the 3nth power of a basic integral. The basic integral is a one-dimensional integral, e to the minus p squared. Now p squared does not mean px squared plus py squared plus pz squared. It just means a one-dimensional variable. E to the minus p squared beta over 2m. That's just this. Integrated dp. All right. I don't remember if we discussed it. Did we discuss Gaussian integrals? We did not. Not this quarter. All right, let's discuss Gaussian integrals quickly. We'll do it quickly. This integral, let's not call it p, let's just call it L, e to, or y, e to the minus y squared dy. From where to where? From minus infinity to infinity. These momentum integrations go from minus infinity to infinity. Can momentum be negative? Yes, it just means going in the negative direction. This integral is just a number. It's a convergent integral, and it's just a number. Okay. Anybody know what the number is? It's just square root of pi, period. Square root of pi. Square root of pi. How the hell do you get a square root of pi in a formula? Well, since the answer is square root of pi, if you want to do the integral, it's smart to do the square of the integral. The square of the integral will be pi. I'm not kidding. That's right. That's the way you do the integral. You square it, and then you can do the integral. You can't do the integral the way it is. You can do it if you square it. Okay. All right. Some other time I will do the integral for you, but not today. Okay. So to do this integral here, it's sort of this form, but there's an extra coefficient in front of the y squared, namely beta over 2m. All I have to do is change variables. Let me change variables so that p squared times beta over 2m is y squared. That just means you've changed variables that p is equal to the square root of 2m over beta times y. That's all. Then p squared will be 2m over beta times y squared, and what's in the exponent here will just be simple. It will be what? E to the minus y squared. But what happens to dp? dp is not dy, but rather dy times 2m, let me put it on the outside, 2m over beta to the power 1/2. And now I've done the integral. The integral is the square root of pi, that's this, times this factor here. Oh, yeah.
Why?
Why?
Isn't there a y term there?
Where? Where is there a y?
Jesus.
Did I do this right? Yeah. I replaced dp by dy times the square root of 2m over beta, which is the same as 2m over beta to the 1/2 power. And now the integral is just the square root of pi, and so this altogether is 2m pi over beta to the 1/2 power. That's it. We've done the basic integral. How many such powers, how many powers of that integral are there? 3n, one for each component of the momentum. So the whole partition function has now been done. It is 2m pi divided by beta to the power n twice n divided by 3. No, just 3n divided by 2. 3n divided by 2. I can't think without my pants. Notice the whole thing is something, yeah, even the n factorial is approximately the nth power of something simple. If we were to have plugged back in the density and all that stuff, this is just the nth power of something. In other words, there's a factor for each particle. We could have done it for one particle and then just taken the nth power of it. And that would pretty much give us the right answer. Okay, so this is the partition function z. It depends on the volume, and for fixed volume, it depends only on the temperature. Volume is a control factor, and beta is the temperature. Now, first of all, let's calculate the energy per particle. Oh, before we do that, let's take the logarithm of it. I want logarithm of z. The logarithm of z is equal to, well, is minus logarithm of n factorial over here. Then there's plus log n log v. N log of the volume, that's from here. And then there is minus 3n over 2 log beta. That comes from here. It's minus because the beta is in the denominator. And then there's plus 3n over 2 log of what? 2m pi? That's it. We could write this, I leave it as an assignment to you to rewrite this in terms of the density instead of the volume in n. You'll find that it's basically n times logarithm of the density. The n factorial and the v combined together to give you logarithm of the density, but I'm not going to do that now. Okay, that's it. That's log of the partition function. Let's first calculate the energy per particle. All right, let's calculate the energy before the energy per particle. Notice that all the interesting terms, well, we'll see what's interesting in a minute. Let's calculate the energy per particle. What's the formula for the energy? General formula, doesn't depend on the fact that it's a free gas, just very general formula, minus the derivative of log of z with respect to beta. Energy is equal to minus the derivative of log z with respect to beta. Well, it's all laid out for us. That's equal to plus 3n. The minuses here and here cancel, and we get plus 3n over 2, and the derivative of log beta with respect to beta is just 1 over beta. What's 1 over beta? Temperature. So the total energy of the gas is 3/2 T times the number of particles, and the energy per particle is just 3/2 the temperature. If I were to change units and use the standard textbook unit convention, I would replace capital T by kT. By Boltzmann's constant times, let's say Boltzmann's constant times little t, 3/2 kT. I won't do that, I'm not going to follow that convention, but I just wanted to point out 3/2 kT is the textbook answer. First of all, where did the 1/2 come from in the formula? The 1/2 came from the square roots in the Gaussian integral. Right? It came from the square roots in the Gaussian integral. Or it came from the Gaussian integral. Where did the 3 come from? The 3 dimensions of space. So basically, there's a kinetic energy per direction per particle, which is 1/2 t. Right? Per direction per particle. The 3 directions of space, if there was 26 dimensions of space, then it would be 26 over 2. I picked 26 at random. It had nothing to do with string theory. I just, 20, huh?
We believe you.
Yeah, no. 26 is the letters of the alphabet. Okay, so E over N is 3/2 the temperature, or 3/2 kT if you like. If you wanted to plug in numbers and use 300 degrees at room temperature, you'd want to plug in the Boltzmann constant, which is 10 to the minus 23 or something, and you would find the energy per particle is 10 to the minus, what, 21 or something like that in joules. So it's pretty small. Okay, so that's the first step, or the first little thing we can calculate. Next, let's calculate the pressure. That's an interesting thing to calculate. To calculate the pressure, we first calculate we want to calculate the derivative of the energy with respect to volume at fixed entropy, but that's too hard. So let's calculate the derivative of the free energy with respect to the volume at fixed temperature. That's a lot easier. Okay, so let's do that. First, we need the free energy, A. A is equal to minus T log Z. And we want to differentiate A with respect to volume, minus it is pressure. Okay, the only term which is going to contribute, only the terms which depend on the volume are going to contribute to this derivative. We might as well throw away everything else. Nothing else will give us a derivative with respect to volume. Remember, we're doing this at fixed temperature. This is at fixed temperature. So at fixed temperature, this is just a constant when I'm differentiating. This is a constant. The only thing which depends on the volume at fixed temperature is this volume term. That's it. That's how easy it is. Okay, let's see what we get. The derivative of T, this is minus T, times the derivative of log V with respect to V. Now, do I have a... Yeah, n log V. And that's just... So what am I writing? I want to write the derivative of the free energy. I should be on the next line here. On the next line, this is equal to N over V, period? I think that's it. No, times T, the T over here. No minus sign, because there are 2 minus signs. I don't know if, can everybody see this minus sign over here? Yeah. There's a minus sign right where my finger is. Minus the AdV is P, but A is minus T log Z. So the 2 minus signs go away, and when I differentiate, I just get N over V times the factor T. There we have the ideal gas law. The ideal gas law P is PV equals NT. Pressure times volume is the number of particles times the temperature. That's the standard ideal gas law. Of course, in textbook notation, this would be PV equals NKT. And then we could write that, if we like, as pressure, we divide by volume, if we like, and we can write that N over V is the density of particles rho kt. So it tells us that pressure is proportional to density times temperature. Okay, forget the K. In my units, in which temperature has units of energy, its pressure is equal to density times temperature. That's the ideal gas law. That's the particle density, not the mass density, but the particle density, right? So, and as you see, we don't need any, we don't need to think about the molecules. We don't have to think about the collisions with the walls. We don't have to, we just mechanically, we mechanically carry out the statistical mechanical definition of pressure, the statistical mechanical definition of energy, all in terms of the most fundamental variable, which is the partition function. Yeah.
How do we get rid of the mass?
Good question. How did we get rid of the mass? The mass, where was the mass in the partition function? It's over here. Differentiating it, it's just a constant.
Right, you just have an overall constant there.
Yeah. Isn't that remarkable? That the pressure doesn't depend on the mass. It is remarkable. Neither does the average kinetic energy. The average kinetic energy is gotten by differentiating with respect to beta. So if you put a bowling ball in a gas, the kinetic energy of the bowling ball will be exactly the same as the kinetic energy of the of a single molecule, of any single, or if you make, yeah, the bowling ball will have the same kinetic energy as the energy of any other molecule. It will have a much smaller velocity. Right. So, yeah, so that's a good point, that the energy, that the mass cancels out of these formulas, oddly. What else is interesting about this formula?
In your notes, you carry along an H bar.
Oh,
Here you didn't
right.
use it.
The H bar is just a convention. It's a convention. I'll tell you what the convention, why there's a convention. The original definition of the partition function as a sum was a dimensionless, let's talk about that a little bit, was a dimensionless quantity. In the exponent, the thing in the exponent was dimensionless. E to the minus beta, beta has units of 1 over energy times energy. This is dimensionless and it's just a sum. So the usual definition of the partition function, the partition function is dimensionless. On the other hand, with this definition here, the partition function has the dimensions of whatever x times momentum to the 3n power are. Now, x times momentum is not dimensionless. It has units of what is called action. All right? It is not dimensionless. To make it dimensionless, what we do is, and it won't change any answers, I'll show you why in a minute, but to make it dimensionless, what we just do is divide each factor of an x times a p by a physical quantity, by a constant of nature with the dimensions of x times p. It doesn't matter what constant, it doesn't matter what we divide it by in fact, but just to give it the right dimensions, we divide by Planck's constant. Every time we see an x bar times p, we divide by Planck's constant, and that gives us some factors of Planck's constant. What will it do in the partition function here? It will give us another minus n logarithm of Planck's constant. Okay. Doesn't make any difference to anything because we're always differentiating the partition function. Makes no difference to anything. Differentiating the partition function to calculate various quantities, or differentiating the logarithm of the partition function, this just doesn't contribute. So
two terms.
it's a convention.
There's only two terms that are important for the derivative.
That's right. It's only two terms in this expression here which are being differentiated. Right.
Probably 3n there, isn't it? Yeah.
Say it again.
Might that be 3n?
No, I think it's n. No, there's a 3n. Yes, thank you. It's 3n. 3n. Okay. In fact, it's kind of interesting if we really did do quantum mechanics, and we did the quantum mechanics of the free gas, the free ideal gas, this term would actually appear there naturally just by summing over states. We would discover it. Yeah, this is a quick and dirty and shorthand way of calculating the effects of quantum mechanics. Does it come into anything? Not really. Nothing interesting. So at least not until we start exploring quantum mechanics. Then it does have an interesting consequence, but or an interesting point about it. What does it do to the entropy, incidentally? It does contribute to the entropy. If we go back to the connection between, remember there's a connection between beta times the energy, the free energy. Well, it would add a constant to the entropy. But again, adding constants to the entropy doesn't change anything. Okay, that is the ideal gas law. It is interesting to calculate the entropy. How would we calculate the entropy? It's interesting to calculate it if for no other reason than to see that it's fairly complicated and that you would not want to try to calculate derivatives of anything keeping the entropy fixed. Let's just look at the entropy. Let's see, there's a formula for the entropy in terms of, I think it's A minus E, and then there must be a beta.
Yep.
I think that's right, huh? All right, so let's calculate that and see what kind of nasty thing we get. First of all, A is 1 over beta log z. That's easy if I know the partition function. In other words, beta times A just gives me log z. Minus, now what's E in terms of log z? The derivative of log z. All, I think, times beta, right?
By the way, I think it's E minus A.
Is it E minus A or A minus E? E minus A? I can never remember. Okay. All right, so it's a sum of two terms. The sum of the two terms, S. S is first of all equal to minus log z. That's not too hard to calculate. Plus beta, or minus, I guess. No, minus or plus? Plus beta d log z by d beta. Okay, now that's not so bad. But if we actually go and calculate it, we're going to find out that it's kind of a mess. It's not too bad a mess, but just for the free gas alone, it has logarithms in it, and logarithms are sort of hateful. It has things which are logarithms and things which are not logarithms. So let's see what it has. It has logarithms of z, which is all this stuff. In particular, the important pieces of it are n log v minus 3n over 2 log beta, plus this constant stuff over here, which is not important when we differentiate it. And then beta d log z by d beta, but this is just the energy. D log z by d beta is minus the energy, so this is minus beta, I think it's minus beta, times the energy, and what was the energy? The energy was 3/2 n times t over beta. Sorry, the betas cancel, I think. The betas cancel? I think the betas cancel. Why did the betas cancel? Yeah, the betas cancel. So this is the entropy, and the entropy involves logarithm of beta. And so if I try to calculate, well, it's just a little bit complicated. In this particular case, if I try to calculate the pressure as the derivative of the energy with respect to volume, keeping entropy fixed, I would have to remember to keep log beta fixed. That's a little bit of a nuisance. It's more complicated than just differentiating the free energy with respect to the volume, keeping beta fixed. Keeping the energy fixed, differentiating the energy, keeping the entropy fixed is a more complicated process, and where you have to remember to keep this fixed as you differentiate the energy with respect to the volume. This is the tip of the iceberg, because this is an extremely simple system, the free gas. Normally, the entropy is a rather complicated and nasty function, and keeping it fixed while you differentiate the energy can be very hard. On the other hand, if you can calculate the partition function, all you have to do is differentiate the volume, keeping the free energy, keeping log z fixed, and that's the fewer steps. So Helmholtz free energy is a good thing. It has all sorts of applications, and its main advantage is that the things that you calculate are generally at fixed temperature. Any questions? Yeah?
Why is it called the partition function?
I don't know. I really don't know. I think I suspect it has to do with, well, there is a thing in mathematics called a partition function, which is the number of ways of summing up. I don't know the origin of it, but it probably has to do with partitioning the energy into these bins there. How many ways are there of partitioning the energy? But I don't know for sure.
Free energy, what's free about it?
Don't know. Again, I don't know. This terminology is historical, and I do not know what's free about it. I don't know. Nothing. I don't know. And it's not the only kind of free energy. It's the Helmholtz free energy. What does it have to do with Helmholtz? Again, I don't know. There's also a Gibbs free energy.
Question, the free energy, Helmholtz free energy, since temperature's in there, does that imply it's an equilibrium, it only pertains to an equilibrium state?
Yeah. Because it has a temperature in its definition. Well, the whole idea of a partition function, now again, it's one of these things, if there are very slow variations, you can ascribe a free energy to small volumes as long as things are varying slowly over distance and time. So, another example, or another general way in which free energy is important, if you have well, let's first take supposing you have a movable partition. This is just an example. A movable partition with gas on both sides. And the partition is free to transmit energy between the two parts of the system. Then it will have pressure on it from both sides. What is the equilibrium configuration? The equilibrium configuration of this partition is when the pressure from both sides are equal. In other words, when the net force on the partition is equal to 0. All right? That means that the derivative of the free energy of the left side with respect to the volume of the left side must equal the derivative of the free energy of the right side with respect to the volume of the right side. But a small change in the volume of the left side will give you the negative of the small change of the volume on the right side. So if we referred everything, let's say, to the left side, this would become minus the derivative of the right-sided free energy with respect to the volume of the left side. In other words, we would write that the derivative of the free energy, left plus right, just transpose to the other side, left plus right with respect to the position of the partition is equal to 0. Okay, we would just put this on the other side, and then the free energy on the left plus the free energies add. Free energy on the left plus the free energy on the right is minimized. Okay. Now, that's at constant temperature. Remember, these things are derivatives at constant temperature. So the meaning of this is the following, that if the whole system is in a heat bath, which keeps it at constant temperature, as the changes happen, the heat bath is enormous. So as changes happen, assume the temperature of the heat bath doesn't change. If the system is in a gigantic heat bath, and we want to find out the equilibrium position of this partition, it's where the free energy is stationary, not where the original ordinary energy is stationary. So equilibrium in a situation where the temperature is held constant. Temperature typically is held constant by being in a big heat bath. If the temperature is being held constant, then the mechanical equilibrium happens not where the energy is minimum, but where the free energy is minimum. That's a bit of a surprise. You might have expected where it's where the energy is minimum. It is not. It's where the free energy is minimum. Now, of course, in saying that you're in a heat bath, it's assumed that energy can flow back and forth into the system here. Okay? So that's a big advantage of free energy, that it establishes where equilibrium is in a system kept at fixed temperature.
But didn't that contradict the assumption that you made when you were deriving the pressure rule, that no energy is going to flow out of the...
No, what we derived under those circumstances, under the adiabatic circumstances, is that you do use the ordinary energy. We've swapped ordinary energy for free energy and adiabatic for isothermal. Adiabatic is harder as a general rule than isothermal. Isothermal means at fixed temperature. So, right, you would get a different, okay, so you would get a different, actually you would get a different equilibrium position if you had adiabatic walls which didn't allow energy into and out of the system. Then the temperature would not be kept constant, and the partition would move, nothing to do with partition function. The partition here would move in a way which would minimize the energy. But if you're keeping it at constant temperature with energy flowing into and out of the system, then the equilibrium is when the free energy is minimized. So that's an important distinction. And sometimes it's really important for some problems, because you get a different answer. You get the wrong answer if you minimize the energy. Any other questions? Okay, mostly what I wanted to impress on many of you, many things. First of all, the ideal gas is an interesting system by itself. But the main thing I wanted to impress on you is the power of knowing the partition function. The power of knowing the partition function. Once the partition function is calculated, a series of almost mechanical steps will derive for you energy, pressure, entropy, fluctuations. We haven't talked about fluctuations in pressure, but that's an interesting thing in itself. How does the pressure fluctuate? And just about every thermodynamic relationship, every thermodynamic quantity can be computed from the partition function by a relatively simple thing of usually differentiating the partition function. So it's a powerful tool. Okay.
For more, please visit us at stanford.edu.